Liquid dielectrics are denser than gases, so they should be better insulators or dielectrics. They also play a role in transferring heat. If we remember back to gaseous dielectrics, what happened when you had high pressure? The gas had a higher breakdown strength. Right, so if you think about it, liquids are very much like a very dense gas. The electrons in a liquid dielectric would not gain energy in the same manner that they gain energy in a gas. Right. Liquid dielectrics are used in transformers, cables, capacitors, oil-type circuit breakers, and reactors. Those are the predominant ones. An oil-type circuit breaker, those are very problematic, and they're causing lots of failures around the country. They're generally being replaced by vacuum-type circuit breakers. Let's look at a couple of oil types. There's transformer oil, cable oil, capacitor oil. The breakdown strength, so let's just look at the transformer oil. It's 15 kV per millimeter, and compared to air, which has an approximate breakdown strength of 30 kV per centimeter. We now start looking at something called permittivity. You would have seen a bit of this in the solid dielectric lecture, but this is quite important as well. And we're defining the resistivity here. It's more easily measured than it is in air. So we're looking at very high resistances, so 10 to the 12 to 10 to the 13. Right, let's look at why I'm saying the permittivity is quite important. If we take just a hypothetical situation, and we've got two materials between an electrode with a voltage V and naught. Material one, let's call it air, or something with a permittivity of 1. It's going to have a gap distance of D1. Material 2, let's call it oil. It's going to have a different permittivity to that of air, and it's going to have a thickness of D2. We know that your voltage can be related to your electric field. In fact, we can split it such that E1 D1 plus E2 D2 is equal to V. We can recall some stuff from field theory. You will recall something called electric flux, D1, and that would be equal to the permittivity times the electric field. So at the boundary between the two materials, for a tangential electric flux, your D1 would be equal to D2. So your relationship between your electric field and your permittivity would be epsilon 1 E1 equal to epsilon 2 E2. Let's just again take a hypothetical case where your permittivity of air, or your relative permittivity, is 1, and that of oil is 2. So your electric field in material 1 would equal to twice the electric field in E2. Right, so that's quite important. We need to look at this here. So for example, in air, your electric field is higher than that in the oil. On top of that, your air has a lower breakdown strength than that of the oil. Right, and I've written that note there. So that's why liquid dielectrics are used, but there are some places where we need to be careful with them. Let's look at a couple of the breakdown mechanisms. So insulation oils are not pure. They contain many impurities, gas bubbles, suspended particles, water droplets, etc. If you think about it, when there's high temperature, it'll break down the liquid particles and turn it into a gas. There'll be a chemical reaction there, and that can be problematic. So the first breakdown mechanism, we're going to look at the suspended particle breakdown, and I'm just going to share a video before we look at it. Can everybody see the video? I'm going to try play it. Just let me know if it's not playing. It's going to be a slow, well, it's a bit faster. All right, can somebody confirm that they can see the video and they can see the movement of the particles?
Yes, sir, we can see the video.
All right, I'm going to start it again. So at the top here, there's a high voltage electrode. At the bottom here, so there's a ground plane. So that would be at 0 volts, that would be at a high voltage. So this is transformer oil. It's in a yellow color. And those particles there are just grass particles. So your electric field will be very high around the electrode and not as high around the ground plane. Must be noted that those are not really conducting particles. It's dried grass. It's just a dielectric with a permittivity. What you can see is that the particles are moving in the electric field. You can see some gas bubbles that popped out there. What you can see here is that the particles have actually bridged the gap. So if those particles don't have as good breakdown strength as the oil, that can lead to breakdown. You can see how it's crossed the gap. Right, let's close that. So the suspended particle breakdown, a particle is considered to be a sphere of radius r with a permittivity of E2. The particle is suspended in a liquid with permittivity E1 and will experience a force given by the equation. Right, so it's the difference in permittivity that's causing the force here. The direction of the force is dependent on the permittivities, but essentially it's the same thing that you saw. We've got two electrodes. The first thing is that a particle is suspended. It moves in the electric field and it starts forming a bridge across the gap. Right, so breakdown will occur along that bridge. The second breakdown mechanism that we'll look at is cavity breakdown. You even saw in that video, or maybe it wasn't clear, but there were little bubbles that came out. So liquids can contain gas bubbles, gas pockets on the surface. There could be changes in temperature and pressure. There could be dissociation of products by electron collisions. There could be liquid vaporization due to corona charges or partial discharges. In any event, the electric field in a bubble would be given by the equation here. EB is equal to 3E naught divided by your epsilon, so your permittivity of your liquid plus 2. That's an empirical relationship. So let's look at it diagrammatically. We've got 2 electrodes again. We've got a number of gas bubbles in there. Those gas bubbles could have a permittivity of 1, whereas your liquid would have a permittivity of 2.3. Right. We can recall that the breakdown strength of air or gas is generally lower than that of oil. We also recall from earlier that your electric field is going to be very different. Your electric field may be enhanced in that bubble. So it is likely that breakdown will occur in that bubble. It could lead to subsequent breakdowns around it, and that could lead to a discharge across the entire gap. Right. I can see that the opinions have changed. Is everybody in agreement that the liquid dielectric is a better dielectric than a gas in general? There's still a few no's there. All right, so I'm not going to push that any further. Are you all happy with the explanations of the liquid dielectric? It's not a very big section. Yeah, so it's not a very big section, but is everybody happy with the explanations? I'm going to stop that there. All right. I'm going to go on to the practical. I will upload this afternoon. I'm not expecting you to come into a lab, but I am expecting you to kind of simulate this stuff any way you can. So the practical is going to involve the generation of high voltage AC for testing an 88 kV XLPE cable, and it will involve simulating 2 different types of generators and determining what the best generator to use on the site is. So the key there, yeah.
Can you please zoom in? We can't see clearly.
Is that okay?
Yeah, it's okay now.
All right. Okay, so we're going to run a couple of simulations to determine which generators are best on site. The first type of generator is a 2-stage cascade transformer type of generator, and the second is a series resonant generator. So you need to consider the following. The capacitance per unit length of the cable is given here. The length of the cable is the last 2 digits of your student number multiplied by 10. Right, so we need to provide a comparison of the generators You need to calculate the voltage required for testing based on the standards. You'll have to look that up. It's quite important that 88 kV is a three-phase voltage and may not necessarily be the single-phase voltage. You have to do a paper design of the AC generators. Just a note there that this is not a test, so all working does not need to be shown. So I'll show you some examples of that afterwards. We need to develop a simulation of the two generators and compare the input power, voltages and currents, as well as the output power, voltages and currents. You would need to discuss the results there and understand your results appropriately. You need to investigate the generators online and find any of the manufacturers that have these generators and further determine whether these generators fulfill your requirements. If the information is available, you can determine the physical size of these generators. Once you've found all the information, you can use your simulated information and results, as well as the online information, to discuss the two generators, and your main conclusion should be what the best generator to use on site is. So the submission must be in the form of a report. So I've set up something for the submission on Moodle already. I'm hoping there's no gremlins. Please submit with the following naming convention: your course code there, and then your student number. I don't mind if it's a Word file or a PDF. Generally, I'd prefer PDF because it would be easier to mark. Right. And then students are warned against plagiarism and copying. Any submissions that are found to have been plagiarized or copied will go to the head of school and then the university proctor. So I'm going to upload that today. But before I upload that, I want to go through some example reports. Right, so this is a report from a couple of years ago. This practical was looking at the calibration of a high voltage impulse divider. So I want you all to try and read that abstract. I'll give you a couple of minutes. Right, so in this practical, what actually occurred here is that we've got a high voltage impulse divider, and we didn't know the ratio of the high voltage to the low voltage, and we used a calibration method. So basically, that's what it says in that first line. Right, so some details about what actually occurred in the practical, and then we determined the calibration ratios, and then we concluded with what we felt was the best conclusion. Right, so what you can see here is it is a summary of the complete report. It's got the results here. It's got the conclusion here. So an abstract is not simply a summary of what happened. It also includes the results and the main conclusion. I'm not saying all the results or all the methods, but you can see here it's very concisely written that those ratios were determined, and the conclusion is that they're not good enough. Right, you can see here an equation is listed and it's numbered. and then it is used here to determine a ratio. There was no need to put figures in here and show you the calculation. It's not a test, it's a practical. Right? There's the figure that was used to calculate that. Right, so if it's not uploaded, I'll upload the sample report so you can get a feel of what is expected. But maybe we can all read that conclusion again, saying almost the same thing as the abstract, isn't it? The other thing that you'll notice is that I've only got 6 sections. I don't have anywhere close to double-digit sections. It's all concise. All right. I'm going to show you another good practical example. In this case, they were investigating the basic insulation level of an insulator. And if you all read that, you can see that the main result is there. So again, I'll upload that one so that you've got an idea of what a decent report looks like. I'm not going to upload this one. This is an example of somebody that's taken another person's work and tried to change the words so it's not picked up as plagiarism. It's both nonsensical and doesn't apply. I mean, in high voltage, a sentence like reproductions were led for a few diverse crown ring outlines and areas. That makes absolutely no sense. Don't try and fit your report to something else, write it yourself. Results demonstrate that corona rings assumes a noteworthy part in scratching off the electric field shaped by water beads. Again, I have no idea what that means. There's no terminology like that in high voltage. Electric fields can't scratch off each other. A disentangled graph of a high voltage protector. Again, I don't know what that means. Just be direct and write it yourself. You can see by the 4th paragraph, I'd given it back. I'd stopped there, and I couldn't continue any further because the writing was so poor.